Beneath the frozen vaults of a distant moon, an ocean stirs in eternal darkness. For decades, we thought we knew how deep the ice goes. We were wrong. And this changes everything we believed about life beyond Earth. 578 million kilometers from the Sun, in the realm of giant planets and frozen worlds, orbits a moon that haunts astrobiologists across our entire planet. Its name is Europa, a small, cold, crack-covered sphere that may hold the greatest secret of our solar system. Beneath its icy shell hides what we've searched for throughout all of human history, a vast ocean of liquid water. And where there's water, there may be life. But in February 2026, everything changed. Data transmitted by the Juno spacecraft turned our understanding of Europa upside down. The ice thickness isn't 10, not 15 kilometers, as we'd hoped for the past decades. Nearly 29 kilometers of frozen water separate us from the sub-ice ocean. 29 kilometers. Imagine 30 Eiffel Towers stacked one atop another. Imagine the altitude where passenger aircraft fly, and all of it solid ice. When scientists first saw these numbers, silence fell over the scientific community, because this number changes everything. Absolutely everything we planned, hoped for, dreamed about. Every mission to Europa, every ice drilling project, every hypothesis about searching for life all require reconsideration. To understand the scale of this discovery, we need to return to the beginning, to the moment when humanity first realized Europa is not just a chunk of rock and ice. It's an entire world concealing an ocean. The Galileo spacecraft in the 90s transmitted images that made us catch our breath. Europa's surface is riddled with cracks, fractures, chaotic patterns resembling Arctic ice fields after spring thaw. These patterns told a story of movement, change, life beneath the ice. Magnetic measurements confirmed. There's something underneath the surface, something electrically conductive, something liquid, salt water, an ocean 80 to 170 kilometers deep, containing more water than all of Earth's oceans combined. This discovery revolutionized astrobiology. Suddenly, life beyond Earth became not science fiction, but a real possibility. After all, on our planet, life originated in the ocean. Why couldn't it emerge on Europa too? But there was one crucial question that plagued researchers. How deep do we need to dig? How thick is this icy shield? Everything depended on this. Because any future mission, any probe, any robot we send to Europa will have to break through the ice. And if this ice is only a few kilometers thick, the task is difficult but feasible. But nearly 30 kilometers? That's an entirely different story. The Juno probe wasn't designed to study Europa. Its primary target is Jupiter, the giant planet with its raging storms and mysterious internal structure. But fate decided otherwise. In 2022, Juno made a close flyby of Europa, approaching just 352 kilometers from the moon's surface. This was a golden opportunity. The probe's scientific instruments worked at maximum capacity, collecting data on gravitational fields, magnetic fields, internal structure. And now, after years of careful analysis, the results are finally published. Gravimetric measurements showed material density at various depths. Radar data penetrated the upper layers, and the picture came together as a unified whole. Europa's icy shell has a thickness from 27 to 30 kilometers in different regions. The average value is 28.5 kilometers. This is nearly 3 times greater than the most pessimistic estimates of the past decade. Imagine you're standing on Europa's surface. Beneath your feet isn't just ice. These are entire layers of this world's frozen history. The top kilometer mangled, broken, covered with scars from micrometeorite bombardments and radiation strikes from Jupiter's magnetosphere. The temperature here drops to minus 170 degrees Celsius. The next 10 kilometers denser, compressed ice, where pressure from upper layers begins creating structures impossible on the surface. Even deeper, a transition zone, where ice becomes plastic, pliable, capable of flowing like a very slow river under pressure from millions of tons of material above. And finally, at a depth of 29 kilometers, the boundary. The meeting place of ice and water, the moment when solid transforms into liquid. But here's the paradox. Europa shouldn't be like this. According to classical models, a moon only 3,122 kilometers in diameter, located so far from the sun, should have frozen solid long ago, become a dead, icy ball, like many other moons of the outer solar system. So why is Europa's ocean still liquid? The answer lies in the dance of gravity. Europa orbits Jupiter at a distance of 671,000 kilometers. Nearby orbit other large moons Io, Ganymede, Callisto. Their orbits are linked by orbital resonance. For every orbit Europa makes around Jupiter, Io completes 2 orbits, and Ganymede completes half an orbit. This celestial mechanics creates tidal forces of monstrous power. Jupiter literally needs Europa with its gravity. When the moon approaches the planet, it compresses slightly. When it moves away, it expands. These deformations occur constantly, over and over, for billions of years. And this friction heats the interior. Europa's rocky core remains warm. The ocean doesn't freeze. Life gets a chance. But new data on ice thickness casts doubt on one of the key hypotheses about possible life on Europa. The thing is, life needs not just water, it needs energy. It needs chemical elements: carbon, nitrogen, phosphorus, sulfur, the building blocks of organic molecules. On Earth, these elements enter the ocean from above, from the atmosphere, with rain, with rivers. But Europa has no atmosphere in the usual sense. There's only the thinnest shell of oxygen, created by radiation-splitting water-ice molecules. So where could Europa's ocean get the elements necessary for life? Scientists assumed the answer lay in a thin ice crust. If the ice is only a few kilometers thick, cosmic radiation can create chemical compounds on the surface, and tectonic processes, fractures, cracks, would transport them down into the ocean. Young fractures on Europa indeed show signs of crustal movement. Dark bands crossing the surface like scars, these are places where material from the depths emerges outward. But 29 kilometers of ice? That's completely different. How can chemical substances migrate through such thickness? This journey would take not thousands, millions of years, if relying only on slow processes of diffusion and convection in ice. And here appears one of the most exciting hypotheses of recent years' cryovolcanism: Europa's ice geysers. In 2012, the Hubble Space Telescope detected something astonishing: columns of water vapor erupting from Europa's southern polar region to heights of up to 200 kilometers. These weren't just emissions. These were fountains of water from the sub-ice ocean, breaking through cracks in the icy crust. If these geysers are real, and repeated observations in 2016 and 2024 provided additional, though ambiguous, evidence, this changes the entire picture. Geysers mean direct contact between ocean and surface, and if there's a path upward, there's a path downward. Organic molecules created by cosmic radiation on the surface can enter cracks, dissolve in rising water, and be transported into the ocean. Moreover, the geysers themselves may bring samples of ocean water to the surface. Imagine, we don't need to drill 29 kilometers of ice. It's enough to fly through a geyser plume and collect samples. This is exactly what the Europa Clipper mission is counting on. Scheduled to arrive at Jupiter in 2030. Its instruments are capable of analyzing the composition of particles in these emissions. If complex organic molecules, amino acids, lipids are discovered there, it will be the sensation of the century. But ice thickness raises new questions. If the shell is nearly 30 kilometers thick, how can geysers even exist? Where does the energy come from to break through such thickness? The answer may lie in tidal cracks. When Europa deforms under Jupiter's gravity, its icy crust doesn't just compress and stretch, it breaks. Giant fractures are created that can extend kilometers deep. If such a crack reaches the ocean, water under pressure rushes upward. Due to low surface pressure and extreme cold, it instantly begins evaporating and freezing simultaneously, creating an explosive ejection of vapor and ice crystals. This process resembles what we observe on Enceladus, Saturn's tiny moon only 504 kilometers in diameter. There, from the southern polar region, powerful geysers erupt, ejecting tons of water ice into space every second. The Cassini spacecraft repeatedly flew through these plumes and discovered in them not only water, but also organic compounds, molecular hydrogen signs of hydrothermal activity on the sub-ice ocean floor. If the same thing is happening on Europa, then the sub-ice ocean may not just be a water reservoir, but an active hydrothermal system. On the ocean floor, where water contacts the rocky core, there may exist hot springs similar to the black smokers of Earth's oceans. In these places, heated water saturated with minerals and chemical substances rises from the depths, creating oases of life even in complete darkness. On Earth, black smokers are places where life thrives without a single ray of sunlight. Bacteria use chemical energy from sulfur and methane compounds. Around them form entire ecosystems. Giant worms, blind shrimp, mollusks, all exist thanks to chemosynthesis, not photosynthesis. If nature found a way to create life in such conditions on Earth, why couldn't it repeat this trick on Europa? But there's one problem. The thicker the ice, the more stable it becomes. The fewer cracks reach the ocean, the less frequently eruptions occur, and therefore material exchange between surface and depths slows down. The ocean may be isolated from space for millions, even tens of millions of years. During this time, the supply of nutritional elements may be depleted. Life, if it ever originated, may fade away. Or not? There's another source of chemical elements, Europa's rocky core itself. Rocks contain everything necessary: carbon in carbonates, nitrogen in minerals, phosphorus in apatites, sulfur in sulfides. If the ocean is sufficiently warm and chemically active, water can leach these elements from rock. The ocean floor becomes a giant chemical laboratory where reactions continuously occur, creating life's building blocks. New data on ice thickness forces us to rethink timeframes as well. How ancient could Europa's ocean be? If the ice shell is nearly 30 kilometers thick, it couldn't have formed quickly. This is the result of billions of years of accretion, freezing, tectonic processes. And that means the ocean beneath it has also existed for billions of years, perhaps since Europa's very formation, 4.5 billion years ago. 4.5 billion years of stable liquid water existence. For comparison, life on Earth originated approximately 3.8 billion years ago, just 700 to 800 million years after the planet's formation. If the timeframes are similar, then Europa's ocean has had enough time not just for life's origin, but for its evolution. Of course, evolution in an isolated dark ocean will differ from Earth's. There will be no eyes, no need to see where there's no light. There will be no photosynthesis, no sunlight. But there may be other senses, other ways of obtaining energy, other forms of adaptation, bioluminescence, like Earth's deep-sea fish, chemosensory organs for finding nutrient sources, perhaps even primitive intelligence capable of navigating the eternal darkness of the sub-ice realm. This thought is simultaneously mesmerizing and frightening. What if right now, at this very moment, 578 million kilometers away, in a cold ocean beneath kilometers of ice, something is swimming alive? What if it's looking upward at the icy ceiling of its world and asking the same questions we ask gazing at the starry sky? The discovery of 29-kilometer ice thickness isn't a death sentence for the search for life on Europa. It's a challenge. It's an invitation to think broader, seek new approaches, develop new technologies. The Europa Clipper mission, which will make about 50 flybys of the Moon, will map every square kilometer of the surface with resolution down to half a meter. It will measure ice thickness in different regions using penetrating radar. It will find places where the ice shell is thinner, where there are signs of recent activity, where the probability of finding geysers is highest, and then landing missions. The European Space Agency is already developing the concept of a probe that can land on the surface, analyze ice composition, perhaps even drill the first meters. This will be just the beginning, because the ultimate goal is to reach the ocean. And for this, humanity will have to create technologies that don't yet exist. Cryobots, autonomous underwater robots capable of melting ice with heat from their reactors and slowly descending through the thickness. Their prototypes are already being tested in Antarctic glaciers in subglacial Lake Vostok, where conditions are maximally close to Europa. But a journey of 29 kilometers is years of work, even for the most advanced cryobot. Years in complete isolation, without the possibility of receiving help from Earth. Every decision the robot must make independently. But when this cryobot finally breaks through the last meters of ice and plunges into the water of the sub-ice ocean, it will be the greatest moment in space exploration history. The first dive into another world's ocean. The first glimpse of what has been hidden from us for billions of years. What will it see there in the darkness? Desolate water expanses, lifeless and cold? Or oases of activity around hydrothermal vents? Or perhaps something completely unimaginable, life forms so alien that we won't even immediately recognize them as living? Juno's new data reminds us, space is full of surprises. Every answer generates 10 new questions. Every discovery shows how little we know. And this is beautiful, because it's ignorance that drives us forward. It's curiosity that makes us build spacecraft, send them on decade-long journeys, analyze data for years. Europa awaits us. Beneath its icy shell nearly 30 kilometers thick, it keeps secrets that could rewrite our understanding of life in the universe. Are we alone? Or is life a common phenomenon, arising wherever there's water, energy, and time? The answer may be swimming right now in Europa's ocean, and we will find it. Thank you for being with us on this journey to the icy worlds of the solar system. If you enjoyed this video, please like it. Write in the comments what you think about the possibility of life on Europa. Support our channel on Patreon. Subscribe to our Telegram channel to be first to learn about new discoveries. Stay with us, and until our next meeting among the stars.